Welcome, Nocturnal Minds, aboard. Your learning journey starts now. So, building on our previous discussion about the scientific method and its sociological dimensions, we now turn our attention to the very fabric of scientific knowledge, the structure of theories. We often think of theories as things we hold beliefs about. Maybe we believe them to be true, or at least empirically adequate. But there's another angle. Theories aren't isolated islands. They're tangled up with each other, with models, and crucially, with the phenomena they claim to describe. Understanding this web is key to grasping how science progresses and how we even manage to explain the world around us. To get a handle on this, some philosophers suggest we need to open up theories like boxes and look at their internal workings. Today, we'll explore two major attempts to do just that: the syntactic view and the semantic approach. We'll see where they stumble, consider a middle path, and ultimately ask, do these analyses tell us what a theory fundamentally is, or are they just clever ways of describing it? Alright, let's dive into the first contender, the syntactic view. Think of it like trying to understand a theory by looking at its grammar and logical rules. It's all about structure represented through language and logic. Imagine a theory having three main parts. First, you've got an abstract formalism, F. This is basically the language used to talk about the theory, plus the rules for deduction, the logical machinery. Within this language you have terms. Some are logical connectives like and or if then, some are non-logical. And these are split into observation terms, things we can see or measure directly, and theoretical terms, things we infer. Like atoms or fields. Then come the correspondence rules. See. These act like a bridge, a dictionary, linking those theoretical terms to observable stuff. Finally, you have the theoretical postulates, which are the core assumptions of the theory, stated purely in terms of those theoretical concepts. So, a theory, according to this view, is simply the combination of these postulates and the correspondence rules T and C. The beauty here is that because it uses formal logic, it neatly fits with ideas like the deductive nomological model of explanation, where explaining something means showing it logically follows from laws and initial conditions. So, the syntactic view looks neat on paper, especially with its fit for the Dean model of explanation. If you can derive a prediction from your laws and starting conditions, bingo, you've explained it. But reality, as usual, throws curveballs. Scientists don't just work with abstract theories, they build models. Think about the classic example, modeling a gas using billiard balls. You know, gas atoms aren't tiny ivory spheres with colored spots, right? They're way smaller, don't have color, etc. But the model uses familiar objects, billiard balls, governed by familiar laws, Newton's mechanics, to understand the gas. It's a simplification, an idealization. Now, the syntactic view hits a snag here. Does this model have the same structure as the underlying theory? Probably not, in practice. And worse, some argue that models often spring up independently of the main theory, sometimes even acting as mediators between the theory and the real-world phenomena. This makes the neat syntactic picture start to look a bit too tidy. How does the syntactic view try to handle these model worries? One way is to say, okay, fine, theories and models are different beasts. Let's study both separately. But then you're back to square one regarding the overall structure. Another way is to insist that models are just mini-theories, small-scale versions with their own postulates and correspondence rules. But then the big question remains, how do all these little theories relate to each other and the big one? More fundamental problems pop up. Remember those correspondence rules? They link theory to observation. What if someone invents a brand new experiment, needing a brand new rule? Does that mean the entire theory is now a different theory? That seems crazy, doesn't it? Introducing a new test shouldn't trigger a theory change. And what about language? Is Newtonian mechanics in English the same theory as in Portuguese? Common sense says yes, but the syntactic view focused on linguistic form gets tangled. Sure, defenders can wave hands about propositions being language independent, but what about cases where changing the mathematical framework feels like getting a genuinely new theory? The syntactic view struggles to draw the line cleanly. So if the syntactic view hits roadblocks, what's the alternative? Enter the semantic approach. This perspective takes a step back from the nitty-gritty of language grammar and focuses instead on what the theory is about. The core idea is that a theory is characterized by the mathematical models it describes. Think of it like this: the theory isn't just the equations or statements. It's the class of possible worlds or situations those equations or statements pick out when interpreted correctly. In this view, the axioms of the theory aren't the foundational statements themselves, but rather the criteria that define which mathematical structures qualify as models of that theory. To present a theory, you just define the set of models it encompasses. This shift draws heavily on developments in mathematical logic, particularly Tarski's work on truth, where truth is defined relative to a model. This approach promises a richer way to capture the messy reality of science, including the complex roles of models, data, and phenomena. This semantic approach has been quite popular. Interestingly, both realists and anti-realists have used it. Van Fraassen, for instance, uses it to define his notion of empirical adequacy. A theory is empirically adequate if its models contain substructures isomorphic to the observable phenomena. Gier suggests we can talk about models being similar to physical systems, using this similarity as a stand-in for truth. The big selling point is that it seems better equipped to handle the complex web of relationships in science, especially the crucial role of models. However, critics point out that it might be too tight coupling models directly to theories. Does every scientific model really just belong to one theory? Morrison and others argue that models often have a life of their own, mediating between different theoretical perspectives and the world. Defenders counter that, hey, nothing stops us from representing both scientific models and their relationship to theories using the same mathematical toolkit, set theory that the semantic approach already employs. Now, if you want to take the semantic approach to the extreme, you end up with structuralism, particularly the work of Stegmuller and Sneed. This is where things get really intricate layer upon layer of set theory. It starts with frame conditions defining the basic concepts. Then potential models satisfy these. Some concepts are internal to the theory, others external. Models satisfying the external ones are partial potential models. Actual models are those that also satisfy the theory's core laws. Then you add constraints and links connecting models within and across theories. The core of the theory is all this interconnectedness. But wait, there's more. You need a domain of intended applications specified by those external concepts. A theory element combines the core and its applications. These can be grouped into theory nets showing synchronic structure, and sequences of nets show diachronic evolution. Even Hollands of theory nets. It's a comprehensive, ambitious system aiming to capture everything. But this towering edifice of structuralism faces criticism. Critics argue that, despite its mathematical ambitions, when it comes to applying theories to the real world, it slips back into relying on linguistic statements about theoretical and non-theoretical properties. Plus, capturing the open-ended nature of scientific application, like figuring out exactly what a theory applies to, seems difficult with standard set theory. Some defenders even try to throw social factors like scientific communities into the mix using set theory, which sounds a bit like a stretch. To tackle the diversity and incompleteness of models, Da Costa and French proposed partial structures. Instead of relations being defined for every possible tuple, they can be undefined for some. Think of it as representing incomplete information or analogies. This allows for a richer representation, potentially even accommodating inconsistent models like Bohr's atom, and defining partial isomorphisms to capture similarities between models and theories. However, even with partial structures, challenges remain. Collier pointed out that the real issue isn't just finding any isomorphism but ruling out the uninteresting ones. Making things partially isomorphic only makes selection harder. The response? Appeal to heuristic factors, like symmetry principles, to guide scientists' choices. This can also address why one idealization might be preferred over another, even if they look equivalent formally. But this brings in informal factors, acknowledging the limits of pure formal representation. This modified semantic view sits somewhere in the middle. Still, the nagging question persists: can we ditch language entirely? Van Fraassen famously said, language is largely irrelevant for describing theory structure. But when we talk about our beliefs, like I believe theory T is true, aren't we using language? Gere points out that claims about model similarity are themselves linguistic hypotheses we judge. So we face a choice: embrace a hybrid view mixing language and models, or revisit Supps's idea of shifting perspectives. Let's explore that hybrid path. Hendry and Psilos start with Hertz saying Maxwell's theory is his equations. Equations are clearly central, but they are language. The hybrid idea is that theories are complex things using both language like equations and models. Equations describe relationships between quantities, but usually describe an idealized model of reality. Models are similar to real systems in certain ways. So, theories are consortia of representational elements. But here's the rub: how do you characterize such a hybrid? The syntactic view had a clear structure for a set of statements. The semantic view had a clear structure for a family of models. Both had components of the same type. But a hybrid has two types: equations and models. How are they related? Interpretation. Interpreting the equations gives you the model. But then, one seems defined by the other. Does this collapse the hybrid back into either the syntactic or semantic view, depending on which side you emphasize? It's not immediately obvious how to maintain a robust hybrid identity. This leads us to another angle, focusing on truth and how we talk about theories. If we're realists, believing theories can be true, how does the semantic view handle this? If a theory is just a family of models, how do models correspond to the world? We need linguistic statements for that. This creates a dilemma. If theories are models, and theories can be true, but models satisfy linguistic sentences, how can the models themselves be true? Da Costa and French propose a solution involving a shift in perspective, inspired by Supps. First, distinguish between extrinsic and intrinsic views. Externally, we look at the structure of the theory, the relationships between models, using tools like isomorphism. Internally, we consider the theory as the object of belief expressed linguistically. When we say I believe he is true, we're in the intrinsic perspective, needing models to define truth. When we analyze interrelations, we're in the extrinsic perspective. The key is not to identify theories with either sets of propositions or classes of models, but to use the appropriate tool for the task at hand. It's about representation, not ontological commitment. This leads to a quietist stance. By focusing on representation, we sidestep the deep question: what is a theory really? Philosophical quietism often involves refusing to give a definitive answer to such ontological questions. Here, the argument is, why worry about the ultimate nature of theories or models if what matters is representing scientific practice accurately? Just as theories represent phenomena, we can use set theory to represent theories and their relationships. This quietism isn't about denying the existence of quarks or genes. It's about being cautious about the metaphysics of theories themselves. The pragmatic line is, if the ontological status of theories doesn't help us understand how science works, then let's focus on what does. The no miracles argument, which argues for the reality of unobservable entities based on predictive success, doesn't apply as strongly here. Positing the reality of theories or models doesn't seem to explain much about scientific practice itself. So, the best move is to turn away from the ontological debate and focus on finding the best representational framework, which seems to be a modified semantic approach. Now, let's switch gears slightly and look at how theories actually change in science. There's a common story told about this. Back in the day, everyone thought science was just cumulative progress. New theories would just generalize old ones, like Newton supposedly synthesizing Kepler and Galileo. But then came the big revolutions of the 20th century: relativity smashing Newtonian absolute time, quantum theory, challenging determinism. These weren't just tweaks, they seemed fundamentally different. Kuhn ran with this, arguing that revolutionary change was the norm, citing the changing views of light from particles to waves to photons. Now, this is a simplified history, but the real challenge since the 1960s has been grappling with this apparent radicality of theory change. Does this constant upheaval shake the very foundations of what makes science special? Specifically, does it undermine scientific realism, the idea that our best theories are approximately true? And does it challenge scientific rationality, the idea that science is a rational process leading towards truth? Kuhn's challenge to rationality is stark. If successive theories contradict each other and operate under different paradigms with different rules, how can we objectively say the new one is better? Isn't this just a matter of one scientific community replacing another? This looks like relativism. Laudon pushed back, agreeing that methods can change, but arguing that we learn to do science better as we do better science. He needed a way to say later theories are generally better, while allowing methods to evolve rationally. His answer was the reticulated model of theory change. Imagine theory T beats rival T under methodology M. Then once TE is accepted, it turns out TE itself justifies switching to a new methodology, ME. It's a feedback loop theory. Success leads to method change, which then influences future theory evaluation. Laudon saw this as a form of normative naturalism, grounding norms in empirical practice. But Laudon's reticulation faces hurdles. Take his example. Wave theory won despite Newton's inductivism, which supposedly shunned theoretical entities. But how could wave theory have been accepted if inductivism was truly in force? It seems like a chicken and egg problem. Also, the term methodology is vague. If any judgment about likely successful theories counts as methodological, then of course methods have changed. Many such judgments are tied to specific research programs. More importantly, Laudon's model seems to assume that core principles of rationality, like seeking empirical support and avoiding ad hoc fixes, haven't changed. Yet, history shows theories gaining support based on these principles, only to be replaced by newer theories that are even better supported on the same principles. Think of classical wave optics versus Maxwell's theory. So the big questions linger. What are these supposedly stable core principles of rationality? And how do we justify those principles themselves? This leads to a classic philosophical puzzle. How do we justify the basic principles of rationality? If we try to justify them using reason, we risk an infinite regress or a circular argument. It seems we might have to accept some principles as fundamental, as dogmas. This is uncomfortable for rationalists. Philosophers have tried various escape routes, arguing that certain circles of justification are okay, embracing externalist views where justification comes from the world, or naturalizing methodological rules so they can be tested empirically. Despite these efforts, the status of these core principles remains debated. Whatever they are, they clearly involve empirical support, and they must somehow navigate the tricky waters of the Duhem problem. Kuhn's concept of anomalies is key here. He argued scientists often treat surprising data as anomalies, puzzles to be solved within the existing paradigm, not as refutations demanding a paradigm shift. This challenges the idea that theory change is always driven by superior empirical fit. Duhem provided a crucial analysis of why this happens. When we test a theory, say Newton's against data, we're never testing just Newton. We rely on auxiliary assumptions about measurement, atmospheric conditions, etc. Often the theory itself has a core and specific assumptions. So, the full test looks like core theory plus specific assumptions plus auxiliary theories plus initial conditions implies result E. If E is false, logic only tells us something in the premises is wrong. It could be the core theory, but it could also be an auxiliary assumption or a specific detail. Blaming the auxiliaries first is perfectly rational and historically productive. And indeed, treating anomalies as puzzles can lead to breakthroughs. Remember Neptune? Uranus's orbit was weird an anomaly for Newton. But instead of ditching Newton, Adams and Leverrier stuck with him, tweaked the specifics, and predicted Neptune. That was good science. But sometimes, treating anomalies as mere puzzles is just bad science, or worse, pseudoscience. Creationists facing the fossil record. They don't revise their theory, they just add an ad hoc assumption: God made the rocks with fossils already in them. Within science too, corpuscular theorists facing wave-like diffraction results could, in principle, invent complex forces to explain it away. Logically possible, but intuitively feels like cheating. The real question is, how do we distinguish between rational accommodation and irrational ad hoc patching? We need a better account of empirical support. A common suggestion is that predictions beat accommodations. Fresnel predicted the white spot in diffraction. Corpuscularists accommodated it. Darwin predicted trends in the fossil record. Creationists accommodated them. Seems intuitive, right? Predictions count more. But hold on, Mercury's precession was known before Einstein. His explanation is hailed as strong support. Time order doesn't seem decisive. Why should it matter? Worrell offers a better distinction. It's not prediction versus accommodation, but non-ad hoc versus ad hoc explanations. Good science involves explaining results using natural assumptions. Bad science involves tailoring special assumptions just to fit the data. Think about creationism. The specific theory explaining fossils is built directly from the fossils. No independent prediction. Contrast this with Newton. The Uranus data led to a revised Newtonian account, which then predicted Neptune, a testable prediction. The difference lies in whether the explanation relies on general principles or is specifically constructed to fit the known facts. Now, let's connect this back to realism. Scientific realists are motivated by the incredible success of some theories, like QED matching experiments to absurd precision. It feels like a miracle if such a theory is completely wrong about what's really going on. Realism says our best theories are approximately true. But here's the kicker. If we accept that past theories like Newton's were radically false despite their success, why should we assume our current best theories, like general relativity or quantum mechanics, are approximately true? Maybe they'll be replaced just as radically in the future. The history of science would then look like a series of near misses, a history of miracles. How can we hold on to realism about current theories while acknowledging the dramatic changes in scientific history? One line is heroic: accept past theories were wrong, but insist current ones are true. But why should ours be immune to future replacement? It seems arbitrary. A more common approach is partial realism. Give up realism about fundamental theories, maybe space-time or the nature of reality, but keep it for lower-level theories, like atomic physics. Or entity realism, believe in the existence of entities we manipulate, like electrons, because we can manipulate them, even if we don't see them. But why believe we're manipulating electrons? Because our theories tell us so. This looks like realism about certain well-established low-level theories. The problem is, the most striking successes, like Newton predicting Neptune, often come from fundamental theories. And fundamental theories, like QM and GR, are expected to eventually be superseded. Shouldn't we be cautiously optimistic about their approximate truth? So, how do realists like Kitcher and Psillos tackle this? They propose realism about parts of fundamental theories. Kitcher distinguishes between working posits, the core ideas preserved through revolutions, and presuppositional posits, the bits that get thrown out. Fresnel's wave theory, the working posit was light is a wave, which survived into Maxwell's theory. The presuppositional posit was the elastic ether, which didn't. The optimistic meta-induction is that these working posits will keep surviving. It sounds plausible, but is it too optimistic? Fresnel's wave idea seems as outdated now as his ether concept. From a quantum perspective, light behaves probabilistically associated with particles. It's hard to see Fresnel's transverse waves as preserved in any deep sense. This line of thought seems to blur into the next major contender. Structural realism, SR, pioneered by Poincaré. This aims for the best of both worlds. It acknowledges the predictive success of theories suggests they grasp reality somehow. But it insists that scientific progress, even in fundamental theories, is cumulative, but only at the level of structure. The idea is that, while our metaphysical pictures of how reality works might change dramatically, the underlying mathematical structures themselves tend to survive. Think Fresnel again. Maxwell's theory ditched the elastic ether, so Fresnel was wrong about the medium. But Fresnel's theory correctly described light as something vibrating perpendicular to its direction. Maxwell's theory agrees structurally, so Fresnel was wrong about the nature of light no other, but correct about its structure transverse wave behavior. Current theories preserve the structural core of earlier successful ones, even if the interpretation changes wildly. It's realism about the mathematical skeleton, not necessarily the flesh and blood details. Is SR defensible? It's certainly controversial. Some feel it's not strong enough realism because it's too cautious about reference. Putnam, for instance, argued realists need to assert that theoretical terms refer to real things, even if approximately. SR seems to waver on this too. It rejects the idea that we have direct access to reality to fix reference. All we have is theory-mediated access. How do you understand an electromagnetic field? SR says the mathematical structure globally reflects reality, and the evidence for this is predictive success. It might feel like waving hands, but it's arguably the most robust form of realism that can withstand the historical record of radical theory change. It respects the pro-realist intuition about success while accepting the anti-realist challenge from theory change. So, wrapping up our whirlwind tour through the structure of theories and the dynamics of change, we've seen the syntactic view's neat logic clash with messy reality, especially models. The semantic approach offered flexibility but faced its own set of issues around identity and language. Structuralism tried to be exhaustive but became overly complex. The hybrid view aimed to bridge gaps but risked collapsing. Quietism suggested focusing on representation over ontology. And throughout the challenge of theory, change loomed large, forcing us to confront the limits of rationality and realism, leading to ingenious but contested solutions like partial entity and the structural realism. Clearly, understanding the architecture of scientific knowledge and how it evolves remains a fascinating and far from settled philosophical quest.